Welcome everybody to the December meeting of the Stockton Astronomical Society. Show and tell. How long have we been doing show and tell? Forever, right? So
we started it with Ed Wright when he was president.
It's a tradition that shall continue. So we actually have a full agenda tonight, so I'm going to get started right away with our first presentation. Couple orders of business. First of all, I'm also going to be passing around a sign-up sheet for refreshments for next year. We're already planning for 2026. So if you want to sign up for a month, jot down your name. And we'll have announcements at the end. And refreshments are back there. Thank you, Jeff, for bringing the cookies and welcome everyone on Zoom. Can you hear us all okay? Omar, Kasey, Ray, Jinka. Okay, Jinka, you're up first actually. So if you want to turn your video on and we'll direct our attention to your presentation. Jinka's first, and then Urvi, and then Jerry, Eric, Omar, Kasey, Pat, myself, and Jeff is the finale. Okay. Very good. There we go. Jinka, go ahead.
Just real quick, Jinka. Jinka, are you sharing any content?
No, I'm just gonna be talking.
Okay.
Yeah. So what I wanted to talk about for my show and tell was about an old piece of equipment that I like. And the old piece of equipment that I'm gonna be talking about is wait, I forgot what it's called. It's the Telerad, yes. I wanted to talk about the Telerad. I don't have it right now because it's in my garage, but I wanted to talk about it because like I appreciate my Telerad more because now that I use the new telescope, there's the Starfinder thing with the red dot, and the Telerad was like I'm more used to it, so I'm kind of grateful for that, and I want to like implant that back into my striking sparks telescope, and that's one thing I wanted to share. Another thing that I wanted to share was like an event that I want to see, and I'm pretty sure that there's a partial solar eclipse in like the August of 2026, and I kind of want to see that through my telescope if that's possible. But yeah, I'm looking forward to that.
Very good, Jinka. Anything else?
No, that's about it.
So that partial eclipse in 2026, have you looked at what its path is?
I haven't like seen its path, but I do know it's gonna be like partially visible. I'm pretty sure that it's fully like shown in Europe, but we can see like part of it in California.
Jinka, do you already have a solar filter for your telescope?
Yeah, I do.
Okay.
Yeah. So I kind of want to see the solar eclipse.
You don't need to wait for the eclipse to look at the sun with your scope and your solar filter. So you can practice as often as you like.
Yeah, I'm looking forward to like go and try it out because I haven't tried it out yet, but it's gonna be interesting. I have seen one at a star party. I think Omar had it to the sun, and it was like on his tablet, like overlaying pictures of it. But I think that's the only time I saw the sun through the telescope.
Very good.
Excellent presentation. Thank you, Jinka. Let's give a round of applause.
Thank you.
Good job, Jinka. Thank you. We'll wait for Urvi. Let's see her there. Do we expect her in person? So we're going to move on down agenda here to Eric. And Eric, are you ready? We'll go to you next. We'll hold off on Urvi and Jerry for just a
There
little
you go.
Okay, let me figure out how to share here now. Actually, I don't need to share. I'm just gonna be doing it by video. So let me leave it as it is. And let me switch over to this other camera bit here. Actually, we'll do this one. All right. What do I have going? My spin frame at the very top there. It really doesn't matter because that's only for everybody else. Zoom. It's a little bit bigger. Okay. Okay. So what we have here is an idea for a telescope that I had about 8 years ago. At the time, I only made a CAD drawing, but I have a 3D printer now. And so I decided I was going to try and 3D print up a little workable demo. It's a proof of concept. Still needs some work, but it's a bit of an unusual design. Try and explain it here. At its heart, it's basically a Newtonian telescope, but it has a third mirror. Primary mirror is down here at the base. There's a 45-degree mirror here, another 45-degree mirror here, and in this mirror, there's a hole in the center for the light to travel back out through the eyepiece here. One of the little cap, the primary mirror. And it's all, like I said, it's all azimuth scope. So what it really needs is, that I didn't bother to make, is a swivel base for it. But it would turn left and right in this direction. And then I have the altitude rotation here. So the light would travel in through the top here, down top 45s, down the primary, and come back up the eyepiece here. One of the interesting features of this design is it's meant to be operated in this vertical position like this the whole time. So the mirror is constantly flat, facing straight up. So it doesn't really need a traditional mirror cell to support the mirror. So that's one cool aspect of it. Another cool aspect of it is the eyepiece should be at a constant height the whole time, coming out the side like this. So given this vertical dimension and the horizontal dimension of the focal length, you can optimize it so that it's at a constant height. And I think it would lend itself well to somebody who is disabled in a wheelchair. So I have a little kinetoscope up here, a little red dot finder that you can mount. It actually rotates a full 360 degrees, but doesn't really need to. It only needs to rotate 90 degrees because you would be able to turn it to the other position with the swivel base. It needs some work. I was hoping it would be a little bit more of a workable scope, but with some design choices I made to keep it relatively cheap, these rods are not very rigid. So, and I thought I was being smart, so I would be able to adjust the height of this with these little thumb screws so that I can fine tune the focal length precisely. But then this also sits a bit caddy corner with the four corners. So I'm chasing my tail trying to get it calming. I was able to get it to come to focus, but I was having to hold it and bend it so that it was right over the top of the mirror, so it's not really usable in its current state. But I think it has potential. I went so far as to 3D print a little threaded eyepiece on here where you can turn this to fine tune the focus as well, but again, it's not really workable. So, because of these old column issues. One of the challenges was to figure out how to get this to rotate, this altitude piece to rotate. So I 3D printed a little solution there where I borrowed the idea from, I think this is called a slew bearing. It has an inner circle that rotates different direction from the outer ring. And traditionally it has ball bearings in it. Then I was like, well, let me just 3D print one without any bearings and figure out if I could get that to work first. And I did, I got that to work. So then I incorporated it into this design. And this is how this rotates. Because I needed to figure out, ordinarily, right, you'd have axis of rotation right through the center, but that won't work because the light can pass through. So I came up with this idea to still have the opening and let the light pass together the primary. And that's basically it. Any questions? Yeah.
Yeah, first of all, that's a brilliant idea. Did you come up with that on your own, or has that been around for a while?
I don't know, but I came up with that thing. I don't know if anybody has done it. I came up with the idea because I was holding two mirror diagonals. And that's basically what this is. It's just two mirror diagonals connected together. And I was like, that's interesting. Let me play around with that idea. And I drew it up. Finally decided to see if that would work here.
I've seen this on interferometers, I've seen it on beam splitters, and this is almost like a Springfield, but I've never seen anything like this.
Yeah. Another cool thing about it, so like I said, I have the front you see, I have a hole in this mirror. But you could easily swap the position of the mirrors, put the hole in this one. And instead of looking through the side, then you would look down. And then maybe you could even have both a visual and a camera here if you had a hole in both of the mirrors. But maybe you'd have too much light loss, I don't know. But that's another interesting thing about it. And then if this, so I think maybe what I'll do is I'll try and redesign this where either I'm using some thicker rods or maybe use some aluminum extrusion or maybe even go so far as 3D print a few more sections in here and make it more of a solid tube to alleviate this wobble issue.
Karen, could you can with that design you could keep the same size mirrors above and increase the primary, or are you limited by the size?
No, that's one of the downfalls. I think probably getting a mirror larger than 12 inches, then you're pushing it. This mirror, the hypotenuse is going to be
right.
Has to be larger.
But it could be larger. The primary could be larger.
It could be.
Yeah, which would be nice if you could make it more stable weight wise.
Yeah, they call that a right Schmidt. When you have a large strip and we run a smaller orifice for a wide field, it kind of self-corrects. We call that a WRIGHT.
I think you could get some math and maybe get some math on some conic sections like a light path film. You can probably optimize so that the hole is as small as you need it to be able to still visually see it through the eyepiece and have a really small obstruction. Ordinarily, your secondary mirror would be a physical surface that is obstructed, but this obstruction is a hole. So it's kind of interesting. Anyways, anything else? Excellent.
The layer was like. I'm curious what a tour of your layer was like. The layer of our mad scientists.
Oh, I'm just gonna go apart.
It's actually,
Gotta be full of gadgets.
it's like on the old Batman show where the hillside opens up and you drive the car in and then there's, right, I did that.
The Vandegraaff generator.
Bones ladder, all.
That'd be
Yeah, there was Newton, the Newtonians, and then Dobsonians, and now there's the Holland. Okay. You guys see that scope up here anywhere else? You know, they stole the idea from Eric. So, Eric, if you don't pass that right away. So, it's going well. We've got several more presentations, and I'm really excited to hear Urvi's presentation. She's been preparing. So, Urvi, are you ready? You are? Okay. You're going to come up here and hold the microphone. Okay. The microphone is so that people on Zoom can hear you. Okay. So speak into the microphone, but we're basically talking to the audience here, and we're looking forward to what your presentation is tonight.
Give me a moment to share it with
Okay.
Zoom here. Okay, I think Zoom can see it all right. Whenever you're ready, Urvi.
Omar, Kasey, Doug, are you seeing the presentation okay?
Yes, they are.
Yes. There you go. You need anything else? All right.
Urvi Kulkarni, I'll be talking about control.
They're very old and they can't hear very well. Speak real loud and into the microphone.
My name is Urvi, and I'll be talking about constellations. What are constellations? What are constellations? Constellations are distant stars that form a shape. There are a total of 88 constellations and 48 are degree. All these constellations have different shapes. There are 9 birds, 2 insects, 19 mammals, 10 water creatures, a constellation creature's hair, a serpent, a flying horse, 2 centaurs, which is like a half man and half horse, one river, and 29 objects, and 14 animals. One fun fact is that in ancient times, people used constellations to map and navigate the night sky. Slide 2, measure constellation. When we discuss about how big a constellation is, we are referring to how big it is from Earth. So astronomical angles to measure the size and distance of constellations. As an example, take 2 sticks that are joined together at once. Spread them apart so each stick is pointing to the constellation's 2 ends. Then measure the angular distance of the 2 sticks.
Very good.
Slide 3. Spotting constellations and report. Constellations help with locating stars and mapping the night sky. One day, you might spot the Orion, but how do you know it's the Orion? You might figure out because the 3 stars are aligned. Because of the 3 stars that are aligned that form the belt of the Orion. Constellations also had a big role in agriculture. Earlier, when there were no calendars, constellations were the only thing that helped farmers identify harvest, new season, and celebrate. Earth's revolution around the sun, causing the seasons like the monsoon and summer and winter, both aspects the seasons day and night that cause people in different parts of the earth to be in different parts of the night sky. Slide 4. The northern and southern. One thing the book I read talks about is the northern and southern hemisphere. Let's talk about the northern. In the northern hemisphere, we can find the Ursa Major and Minor, along with Cassiopeia and the Polaris. Next to Cassiopeia is the Anzaldua galaxy. Beside it is the constellation Pegasus. Now for the southern. In the southern hemisphere, You can see sailors eclipsed by the star in the sky. You may also see Canis Major next to the horizon. In Canis Major, you can see a dwarf galaxy, and you can see two stars, Carina and Canopus. Canopus is the second brightest star in the sky. Here are the stars of the hemisphere: Carina, Canopus, Vela, Plutus, Argo, Nimbus, and the southern cross along with Alpha. Slide 5. The Zodiac. There are 12 constellations which lie in the blue plane of the sky known as the Zodiac. The 12 zodiacs are Aries, Taurus, Gemini, Cancer, Leo, Virgo, Libra, Scorpio, Sagittarius, Capricorn, and Aquarius, and Pisces. But how do we know what are zodiacs? For example, a person born on March 21st to April 19th will have Aries as his zodiac. So each and every zodiac has a time period. But why is Aries considered the first zodiac? This zodiac means Urvi after a harsh winter and an important time in Advent. Each zodiac also has a planet. Mine is Pluto because I am a Scorpio. In conclusion, sharing this book highlights creative sparks that can inspire others to dive into the deeper scientific study of constellation, guided by experts who know all about it. This is my presentation. Thank you for this.
Hold on just a minute, see if we have any questions for you.
Yeah, what grader?
Fifth.
Good, very cool. That's cool.
Corda celebration. Corda celebration. Mountain.
And mountain ones, yeah.
I got one for you. What is your favorite constellation? You have one? I have one. It's my birthday. Leo.
It's not the goat, is it?
No. Jerry, you should not say that. What is your favorite constellation?
Oh, Sagittarius, of course.
My favorite constellation is the dolphin, the cloud dolphin.
Is what?
The cloud dolphin, like the dolphin constellation.
Dolphin?
Dolphins.
Yes, dolphin.
Yeah, see? Look good. That is very nice. We would like to offer a deeper introduction of Urvi to the club. She's been very active since she began. Come out here.
Use the microphone.
Yes. I'm going to steal the microphone from you. So as I said earlier, you can hear from the microphone. Well, Urvi's been very active in the club since she began in March. And so we want to offer everyone a little bit more of an introduction for her. She is the daughter of Anita here in the corner and Sarah. As she just mentioned, she's in the 5th grade, school in Mountain House, and she's been very active in the club since she first came to a meeting in March. We hear that she wants to be an astronomer and wants to learn all about the objects of the sky. Now, she's drawn the attention of 2 of our members who had a few things to say about her. Kasey, yeah, Kasey Foley says Urvi needs to clean her room. No, she said Urvi is a motivated young lady who shows real interest in astronomy. When Urvi and I are working together at star parties, Urvi is an enthusiastic learner who asks detailed questions about the night sky and shows great promise and a real love for the stars and sky. Doug Christensen says, since April of this year, Urvi has been a regular volunteer in our school outreach events. I believe her volunteer track record is second only to Eric Holland's. Putting the rest of the club.
So the rest of the executive committee decided that Urvi needs to have a telescope. So we've awarded her a striking sparks telescope. It's our 22nd telescope. Is there a telescope with Urvi's name on it? Oh, yeah.
Telescope. What do you think about that?
Jerry, can you move the podium? Thank you.
Sorry about that.
Here we go. This is our 22nd Striking Sparks telescope. It was donated to the Striking Sparks program by Susan and Michael Leary.
Right.
Michael is a past president of the SAS, and his wife have been ardent supporters of the Club and Striking Sparks program. This, in fact, is their third telescope they've donated to the Striking Sparks donation.
I can focus, work your way up this way. Please. And Anita, you too.
So we are very fortunate and grateful to be the targets of Susan and Michael's attention and generosity. Thank you very much.
I did a photo op here with you guys all in there. Very squishy on in there too.
Yes.
Stockton Sparks. Chairman.
Urvi, what's the first thing you're gonna look at with your new scope? The stars, okay, great.
Not for a while.
Okay.
Something bad.
Give her a round of applause.
Oh, you want me to do that one too?
Right up there.
Okay.
So, here's the IRS certificate.
Were you able to get the picture I sent there?
Yeah, give me a second to reshare it here for you, Jerry. This one here.
Yes. Are we ready?
Oh, I'm sorry. Let me drag this. There we go. Take it away.
Recently, Jeff Baldwin shared a photo with a few of us. This is a photo of the sun taken at night. So the camera had to be pointed into the ground, which is the direction you want to look for the sun at night, right? And the idea is that this was taken using neutrinos. And so when I first saw this, I thought, well, that's just preposterous. Neutrinos do not interact with matter. So how did we develop a camera that can take, that can photograph them? And then I thought, oh, I know of such a place actually. It's called Super Cameo Conde. And that is actually where this picture was taken in 2007. So our discussion went on for a bit and eventually led to me volunteering to do this presentation tonight. So neutrinos are a subatomic particle that rarely interacts with normal matter. They do not interact with the electromagnetic force, which is the force that actually gives our world its solid structure. And they do not interact with the nuclear strong force. So they don't normally, even if they get very close to a nucleus, will be unaffected by forces there. The billions of them pass through your body every second. We'll never notice. They pass through the planet mostly unaffected. The sun produces them. Any object, any nuclear reaction will produce lots of neutrinos. And so, in fact, supernova, in a supernova explosion, 99% of the energy is carried away in neutrinos. So how do we detect these neutrinos that don't interact with matter? Hardly at all. We are fortunate that occasionally, if you have enough of them and they go through a massive enough object, they will occasionally being around a little bit, knocking an electron loose here and there. If a neutrino happens to collide with an electron, it will accelerate that electron to a speed faster than the speed of light. In this case, the speed of light in water. So superconductivity is a large, massive object that's hidden inside another large, massive object. It's a large tank of water that is buried 1 kilometer below the surface of the Earth in an abandoned mine. The tank holds about 50,000 tons of water. It has over 13,000 photomultiplier tubes all around it, looking for the faintest bits of light from these collisions. It's 39 meters in diameter and about 41 meters high. And I mentioned 1,000 meters underground. Like I said, so when a neutrino collides with an electron in the tank, it accelerates that electron to a speed faster than the speed of light in water. So we're talking this giant water tank. It's designed to capture any collisions that happen to occur. You might think nothing can travel faster than the speed of light, but that only applies in a vacuum. In a vacuum, the speed of light is 3 times 10 to the 10th meters per second. And as far as we know, nothing can travel faster. In water, however, light bends, light slows down. The evidence of that, if you put your hand in water, the image is slightly different, right? You put a stick in water at an angle, you'll see that the angle appears to bend where it meets the water. So light bends in water is evidence that it slows down, and the speed of light in water is actually about 2.25 times 10 to the 10 meters per second. Still incredibly fast, but 25% slower than it was in a vacuum. So there's nothing that doesn't allow another object to travel faster than that speed in water. So this electron does. So when you move faster than the waves in your system, think about a jet moving through the air. Let's say it's moving faster than the speed of sound. So it's racing ahead of the sound waves behind it. You see it, when you first see it, it's absolutely silent. But the waves behind it kind of form a wake behind the jet. And when that wake hits you on the ground, you hear a sonic boom. We don't hear so, I heard them all the time when I was a kid. We don't hear them much anymore. But this sonic boom, the light version of that is not quite as impressive. But for an electron moving faster than the speed of light in water, it will produce a ring of blue light, very faint, and it's called Cherenkov radiation. And that's what the photomultiplier is for. If they detect any of this faint blue light, Cherenkov radiation, they can figure out where the neutrino came from that caused it. So we don't actually observe the neutrino. We don't observe the electron. All we observe is the results of the collision, which is this faint blue light. And Marshall, can't think of his last name. Marshall Merriam was a nuclear physicist, and so he saw he experienced this Cherenkov radiation personally. He observed it in water tanks and nuclear reactors and such. So the idea then is we see you aim your camera, in this case, at the sun at night and stick around for a while. This image took 503 days. to form. That's like leaving your film exposed for 1 and almost 4/10 of a year. Which is crazy, but that's how long, since these collisions between electrons and neutrinos don't happen very frequently, that's how long it took to gather enough evidence for a picture, enough of these pigments for the picture. It's not real color. The white in the center, that just indicates that's the highest number of collisions. That said, the photomultipliers to tell where the neutrinos came from. So they all came to form the pixels in the center. Outside it is yellow, slightly fewer collisions, orange, red, and so forth. So this is not a true color picture at all. Just shows the density of collisions of the neutrinos in this experiment. So basically, that's how you take a picture of the sun at night. A little bit more about our Kamiokonda guy. The Super Kamiokonda. They call it super because it's like the fourth iteration of the original experiment. It started in the Kamioka Observatory, which is an underground water tank. It started with a smaller tank, so it's just the Kamioka, how was it called? Nuclear decay experiment. Over time, they just shortened nuclear decay experiment to NDE, so it's a Kamioka NDE. Then they just put NDE into the name, so it's Kamiokonda. This is an abandoned mine shaft. Evidently, there is quite a bit of poisoning due to this mine. Some cadmium was leaked into public water sources in nearby towns and whatnot. So they thought best to close it up and use it for a research facility.
Where's it located?
I forget the name of the city. It's in Japan. Guido, little town, Tito or Guido. But it's easy to look up. You can't visit it. It's not open for tours because the nature of the work is done there. Special groups can get in, but there are, if you want to visit it on its website, it points you to different museums that have information about it. The website's quite interesting. I'm taking 10 minutes or so here. And on the website actually says, understanding neutrinos in 5 minutes. Oh, wow. Other interesting thing though, gamma rays from highly energetic objects out in space are detected in the same way. Gamma rays collide with molecule atoms in the atmosphere. Electrons are accelerated to a speed of light, to a speed faster than the speed of light in air. Because when light hits air, it slows down a little bit too. So it leaves a little bit of a buffer for things to go in that range that would produce this Cherenkov radiation. So that is how we detect gamma rays. Questions? Yes.
Okay, so on this picture of the sun here, it looks like a disk. You might think, well, that's the sun, but I'm theorizing that the helium sphere, the shell of the helium sphere where the fusion is actually happening, is probably where the neutrinos are coming from. That maybe we're only looking at the size of the helium core of the sun rather than the sun itself.
Oh, certainly. Certainly. It's the nuclear fusion that's creating the creating those neutrinos. And they don't all travel in a straight line. We have the center is the region where you get the highest number of collisions, and it just kind of gradually tapers out away from that.
So perhaps the sun is this big in the picture instead of this big. Because that's the core of the sun.
Right. Yeah. Right. Very true. So not an accurate photo in the sense that you would normally think of. The only kind
And
of
it's
photo.
probably a Gaussian curve type of picture.
Oh, of course. Yeah.
Jerry,
A while back, we had a presentation from some scientists in Antarctica. And they were doing neutrino detection in Antarctica. Do you recall that? So they didn't have like a big tank of ultra pure water they were using. Neutrinos were passing through the Earth and they were detecting them. Do you recall?
They had a giant block of ice underneath that computer.
The ice was capturing the neutrinos.
That would be my guess, yes. And that's, as much as I can remember from the talk, that's where I think the detector was the ice.
With the natural ice. Gotcha.
Jerry, you said something that didn't click for me. You said it took 503 days to generate the image. Is that a series of collisions, or did it take 503 days to capture this one?
Oh, no, this is quite a number of collisions.
Okay.
So think about your photographic plate, photons are colliding with, right? The longer you leave it open, the more photons are going to collect. Only you don't have to wait 503 days, as you did here.
Okay, thanks.
Done.
Excellent presentation. Thank you, Henry. It's great. You are welcome. Stay out of the rare neutrinos, they don't seem like they're very friendly. Okay, benign. Omar, you're up. Good to see you.
Hey, good to see you. Yeah, okay. So my presentation is going to be very short, and I just kind of been working on some. Well, I actually haven't been working on anything other than work. So earlier in the summer, though, I did start a project that was astronomy related, and that was to try to save some time for doing astrophotography by putting in a semi-permanent pier in my backyard. Once my neighbors decided to cut down their redwoods, I was like, hey, I can see the sky now. And so I looked at the best spot in my yard, which is a tiny yard, to maybe put in a permanent pier. But my wife was not really thrilled about me putting in like something that's sticking out of the ground that sits, 5 or 6 feet tall. So I made a compromise and I said, well, what about a semi-permanent pier? So I didn't even know what that was. So I started looking into it and I decided on, let me see if I can share this here. I decided on going this route, and it's I guess they call it a safety bollard. It's one of those things that they put so that you don't back into like a fire hydrant or something. I don't know. It protects you in various areas. And so what I did was under the bricks and under the rock, I just buried a 20 by 20 by 20. I just filled it in with concrete, just a hole, 20 inches by 20 inches by 20 inches. And I stuck some bolts out of it. And so if I ever need to, if my wife says, hey, it's time to get rid of that thing, I can just undo those and just sweep the rocks over it. And then it's gone, but it can be back very quickly. And so I had to learn a few skills like welding, and I did not learn that skill very well. You can kind of see, and I left it out, and so it's starting to rust. I'm not done with this yet, but the bolts here are for leveling, and I just welded a 1/4-inch plate to the top of it. And then I had to weld this kind of little platform up here to sit the mount on. And this bolt here sticks up through there, and I tighten it and make sure it's aimed north, and it does pretty well. And I was actually able to get one imaging session in, And it just whatever I was able to see at the time, I decided on NGC 7331. And just because I happened to think it was pretty, but I did not know that there was a supernova going on apparently at that time. And so I was actually, when I was looking at that, and then I read that there was, a supernova visible, I was shocked that in my image, and I'm still working on this one right here. Here it is. This is the color's a little bit funky. I don't know how to fix that yet, but here's the galaxy right here. And right here, this is the supernova. And I didn't find that out until several days later when I started looking at it. And then sure enough, there it was. I happened to catch it. So, I mean, the timing worked out because I don't get any time for anything. And that's the one astrophotography thing that I did this year. And I caught a supernova. So, pretty thrilled about that. Other than that, not much going on except when the weather clears out, maybe in May, I'm excited about my new binoculars. I got some 7x50s, so that'll be nice. That's all I got.
All right. Excellent. Do you have any questions for Omar?
Omar,
One quick
I have a question.
Yeah, okay.
How close is that pier to your fence? It looks really close.
Okay, yeah, so I wasn't going to mention that, but you asked. So let me go back to sharing again. Originally, this little top hat right here, this platform, was in the center of this 12 by 12 platform, or the top plate. And when that happened, when I had it mounted on there, it actually did an unscheduled meridian flip and it hit the fence.
Oh,
Yeah, and that actually did some damage to my mount. I was able to get in. I actually had to take apart my mount. And I mean, it was close. I'm talking about like an inch. So
oh,
that's when I undid it. I took it off. I had to get the angle grinder and take it off and redo it. And this time I put it on the front edge. You can see it's right up against the front. And that bought me the space that I needed with enough back focus. Yeah, so it had just enough back focus to clear the fence if it does a meridian flip. So good question. Yeah.
you're able to go 360 degrees then.
Yeah.
That's
Yeah.
incredible. That's a great idea. I love that.
Yeah, but I was looking, I was like, man, that's really close. And that brick line is the problem. I couldn't go any farther away because of the brick line. So yeah, I found out the hard way. It was just that much.
Great job, Omar.
All right, thanks.
Ask you to teach me how to negotiate with my wife.
Hey, you know what they say, right? Better to ask for forgiveness type of thing.
Yeah. Yeah. Okay. All right, Kasey, you're up next. So I'll turn it over to you.
Okay. I think Eric has slides for my slides.
Yeah, give me
Yeah, he's shifting gears here.
Okay.
give me 1 second to bring up your slide here and share
I'll
it.
give you all the opportunity to thank Kasey for not being here tonight.
Yes, you're welcome.
Kasey, I hope you're feeling better and it doesn't catch you like it has so many of us.
Yeah.
Okay, I think I'm sharing, Kasey.
It's perfect. Thank you. Everybody can hear me okay?
Yes.
Yep.
Okay.
Yes.
So this will be about a minute-long presentation. This is a book that I read in the past year that I fell in love with. It's possible that everybody in the room has read this book because it came out in the 80s, I think 87, and I guess became like some kind of little phenomenon and then went out of print. And then they reissued it with a different publishing company in 97. And a few months ago, we went to my favorite bookstore in Santa Rosa. And I went to the astronomy section after the birding section, of course. And saw this book, and I love Richard Preston. If anybody knows him, it's embarrassing because he's written books like The Hot Zone and Demon in the Freezer and got a lot of flack for it because it wasn't entirely accurate. So I was kind of concerned about this book, but I just like his style of writing. And everything I read about it said it was very precise and extremely accurate. So, oh, we can go to the next slide, please. What happened is Richard Preston spent a year at the Palomar Observatory. I want to stop here for a moment. This I took a picture of because they were celebrating 75 years of discovery, and it was only 2 years before we were doing it. And I thought I was amazed by that. We stopped by the observatory on our way back from the eclipse in last year, and I saw that, and I thought that was really cool. So we came to our meetings, and we were doing the same thing, just 2 years difference. So anyway, that was cool. Next slide, please. So when I do that, I get sidetracked. But I just wanted to point out that this book is written about, like, the main star of this book is the Hale telescope on Mount Palomar. And it's the 200-inch, it's called the Big Eye. And it was, the book was written in a year's time that Richard Preston spent with these guys in the 80s, kind of living with them as they got their telescope time and living just like them, eating just like them. And so it's a book just about a day in the life of these astronomers and how different they all are and how the telescope, I mean, he writes about how the telescope was conceived and then created and constructed and managed and then maintained. And it's unbelievable. I mean, the stories are unbelievable. And I've been obsessed with this telescope. Well, it was the first observatory I ever visited for 35, almost 40 years ago. And this is the t-shirt I got back then, 35 or 40 years ago. And on our trip back, I mean, last year, then I got this new shirt and my little mug. And every time I buy things from the observatories that we visit. And so this is the one I visited twice. And so I just was obsessed when I found this book. I couldn't believe it. And I was just beside myself reading the book, and the writing was really good. But I also read on cloudy nights from a bunch of people that also loved, nobody didn't love that book. So I just wanted to share it because I think if you haven't read it, you really should read it. I mean, I read it probably in definitely less than a week. It might've been 3 days, but if you just sit there, if you have a day off, like you're homesick, you could probably get through it. It's easy reading and just really entertaining. So I'm going to read what I wrote to say about it. Oh, go to the next slide, please. Sorry. And yeah, this is George Hale. So he is the one that came up with the concept of this on Mount Palomar. He's also responsible for the telescope on Mount Wilson, the 100-inch. And it talks all about the life, I mean, kind of quickly about George Hale and the issues that he had to deal with. And it turns out that by the time the telescope was completed, which was 1948, he had passed away 10 years earlier. He had a bunch of complications. And so he never got to see it develop. They named it after him. Obviously, a lot of people were involved in the development of this telescope, but it was his thought process that created it. And he's an amazing person. So next slide, please. So I'm going to read this. This book chronicles a behind-the-scenes year in the life of the professional astronomers who expanded our knowledge of the universe. They used the 200-inch Big Eye and then an 18-inch Schmidt telescope that was also there called the Little Eye to search for and create cameras to photograph quasars, comets, and asteroids. So they were looking for the beginning of the universe. I mean, the beginning of time, basically. And these guys, these characters in the book, the way they're written about, you feel like you're there, you feel like you know them. So the guy, Juan Carrasco, he operates the Hale telescope. I'm not sure if he still does because 97 has the new forward in the book and he was still doing it then. And he was previously a barber. And then he got this job to operate the telescope and he will not let anyone else touch it. No astronomers can touch it because they'll mess it up. So, and it's very sensitive, obviously, the telescope. So there's a whole chapter about Juan. And then James Gunn between James Gunn and the Shoemakers, I mean, they were my favorite characters. James Gunn is an amazing, I don't even know what to say about him. You just got to read about him. He's an amazing person who created the camera for the Hubble telescope. And then with the extra pieces, the CCDs that were left over from the Hubble, he just brought them back. They're from Caltech. He just brought them back and built the telescope to use on these telescopes on Mount Palomar. He reminds me a lot of Jeff, actually. I was thinking, Jeff, if he doesn't know James Gunn, he should meet him because they're very similar in the way they use scraps to build things out of garbage. I mean, James Gunn literally went through trash cans to get parts. And Don Schneider, he's the one that created the software to use in the cameras. Telescopes work. And then Martin Schmidt, he was a Dutch astronomer who was very proper. So he didn't really, when you look at the personalities between these people, it seems like they would really not mesh, but it's really amazing how they all get along, and it's really funny to read about it. And then Carolyn Shoemaker and Gene Shoemaker are the famous comet and asteroid discoverer people, and they're great to read about. And they're just like regular feeling people. I mean, just like normal people who drive from Arizona to almost San Diego to get their time on the telescope whenever they do. That's just drive over there. And it's just funny. Just everything about this is funny. So I just want everybody to read this. And there might be a gift at the installation dinner that's one of these books. But I had to get it from the used bookstore because it was out of print. I thought. So it's on order. I'm hoping to have it. So it'll be one of the prizes. So that's my story. I'm sticking to it.
Yeah.
Excellent. You got us anxious to get that book. Check it out, Kasey.
Kasey, we were really only seeing the content being shared, not you. So if you want to take a second, show your shirt again.
Oh, here it is. Can you see it?
Yep.
Okay, there's that. And this is the shirt I got 35 years ago.
Oh, very cool.
Mount Palomar.
She's
And
wearing
then-
the telescope.
And my, oops, right here, my coffee cup.
Very good.
Excellent.
See, we need that kind of stuff too to sell to people. So just saying, I'll definitely buy all that stuff.
Kasey, I second you. That's a great book.
Oh, great.
I had a 20-year-old version of that. One of the things that blew my mind was if I remember correctly, a lot of the final grinding that they did on the mirror with their thumbs.
Oh my gosh.
Yeah.
Yeah. Yes. And they used all of this magic. I forgot what they call it now. Magic dust. It's funny. I mean, it's just funny the way they write about everything. It's just amazing. It seems impossible. It's impossible that it exists.
Any other questions or comments for Kasey? Let's give her a round of applause.
Yes.
Oh, so just a quick, yeah. Yeah, this is my, honestly, if you look at my laptop for years, this was my screen saver. I just love this picture.
I need to reshare real quick.
Oh, go ahead.
Okay.
It's just for pinch.
I'm sharing. Go ahead.
Okay. So, the note there shares, William Andrews took this on December 24th, 1960. I love this picture. Frankly, it's always inspiring to see this. And just to know what we are, because we kind of, our egos go beyond what we really are in the universe. But Eric, if you go to the next page, I was thinking about this picture, and I always think about that being the first picture here from space. But there was a prequel. In 1966, Lunar Orbiter 1 took this picture. The orbiter had its own film processing unit on it. So what it would do is take a picture, process the film, scan it, and send it back to Earth. And I thought that was pretty cool. And I thought, okay, 1966, I was 5. That must be the earliest picture of the Earth from space. So then I dug a little bit deeper. If you go, Eric, to the next page.
Where's my mouse? There we go.
Oh, a little bit more background on it, but a little bit more data on what this image was and actually how they took it. And really the purpose behind it. Those orbiters were set up so we could identify appropriate locations for landing on, so we could continue our exploration there. And sorry, Eric, to go to the next page. But there was a prequel to the prequel. So in 1946, we had captured a V2 rocket number 13 Germans after the war. And we launched that rocket from White Sands, Mexico, with a camera. And that's the first image taken from space. Did this come through as a video, or is there a link on it? No.
No.
I'll have to share it with you. I thought that came through on the document.
Well, maybe it did, but I converted it to a PDF, so no.
Oh,
You didn't explain there was a video.
I'm sorry. Yeah, so there's actually a video that was a video that this was called from, of the launch itself and the V2 rocket. And it has a beautiful 1950s voiceover, like you know, that we heard on everything else that was put out at that time. The video itself is interesting because as the rocket launched, it went into a spin. So I would, I'll share the link on this, but I would caution you to not watch it immediately after having dinner, because it will turn you. But it's one of those great old videos where the scientist approaches the box on the ground after the rocket has landed and opens a box that's crushed and pulls out the camera and says, "Here's our image." Of course, in a full suit tie. So, but that's I was unaware of this and this early footage. So just wanted to share that because I think it's interesting, and frankly, I still love Earthrise, but there was a prequel and a prequel to Earthrise that happened back in '46. That's all I had to share. I don't think I had anything else to share.
Maybe at the end, if I can figure out how to get the audio to play, I'll go back to your original.
Okay, sure.
And those were film pictures, not digital.
Correct. Yep. Yeah, so it was all filmed and culled from that. And
Was it black and white film?
yes. Yeah.
You know, I think they've used that footage on a number of 50s science fiction movies.
Oh,
When it goes up and I mean it's spinning.
yeah. Yeah, and it really was the start of our program. The V2 rocket was what the Germans had developed for producing in World War II. And we managed to collect some of the V2 rockets and for our initial exploration and development. And that's all for you.
Excellent. Thank you, Pat. Okay, we're drawn to the finale. You see the mirrors up here. They need a lot of explanation, don't they? Binoculars. So Jeff Baldwin, our resident telescope nut, emphasis on the nut part, has arrived here with plenty to show us. And Jeff, I'm going to give you the microphone.
So you can talk to everyone on Zoom as well.
Hi, guys. How do you pull that off? Just, I'm gonna let you pull that off. And so my first question is, can all you guys in Zoom land hear me okay? You're still awake?
Yes, yes. I can hear you.
Okay, good. Alrighty, so I no longer make monolithic mirrors, now just doing meniscus mirrors, because that's the way it is now. So are you operating the camera and moving around and all that? Okay, good. So meniscus mirror is shaped like a contact lens. Instead of being flat on the back, it's thick, curve in the front. If you can see, it was plate glass that put in a kiln and then slumped into a curve, so it's uniformly fixed up the thing. So when you put on the machine, it would wobble. So I cast the curved back to a glass and plaster mold, then ground them together so they are co-spherical, so that it can go onto the machine and spin around without wobbling or wobbling. And so that's what it looks like it's on the machine. So when it's all together like that, it's like one big thick monolithic glass. But then when you're done working the mirror, it's now such a light mirror, 20-inch mirror holding with one hand is crazy light. I can't remember what it weighs, it's nothing. So anyway, that is a meniscus mirror. It's not done being ground to 80 grit yet, so it's close. This is the tool I'm grinding it with. And it sits on like that. And on my machine, the quill holds that hole. The thing spins, turns, grinds the mirror. So I grind it with thick grit and then small grit, and then I do it with polishing, then I figure it, then I silver it, and then it's a done telescope mirror. So now that will be a 20-inch f3.3 telescope. The whole thing's going to weigh 40 pounds. Pick it up with one hand, walk away with it. So that'll be my little dude telescope. Then I have big dude. And so I have 42-inch meniscus glasses here. And I was going to do 40s. And I'm going to kill them. I want to talk to Mel Bartels about making a slumping dome for 40-inch f2.7. He said, well, you know what? I got a couple of 42-inch f3s. I'm not going to make them. You want them? I said, what do you think? You know? So we made a deal and I got two 42-inch f3.0 mirror planks. They're also meniscus. They're very thin. That's going to be kind of an issue, but we think we got it all figured out. But the little dude's going to be the proof of concept, and the big dudes will be the real deal later on. So I'll have two telescopes. One will be little dude, which will go to the Oak Grove Star for any kind of stuff. And then I'll have big dude, which will go to the Peddler Hill type of stuff. So the next question is, how do you support a thin mirror like this? Here we go. And the answer is, when you have a telescope mirror in a cell, you have back support. So I have an 18-point flotation on here, so it distributes weight throughout it. But then you usually have things holding the edge of the mirror. But because these are thin mirrors, I can get to the center of gravity of this one, but on that one, I can't get to the center of gravity because it's behind the rear lip. So if you were to contact it there, it would bend the mirror and it'll warp out of shape. So I made a puck. That puck is going to get glued onto the back of this mirror. And it's going to, I'm going to hold the weight of the mirror on that puck with a strap. So it's going to just hold the mirror like that with no edge support. So that'll be the transverse support. And when the telescope looking up at the sky, the 18 points will be the longitudinal support. So this will probably deform a small area in the middle of the mirror, but my secondary mirrors can be that big, so it should hide the deformation. So that is the theory of how I'm going to support this meniscus telescope mirror. Oh. I just got these welded today, Mike Studers in Tracy. So this is going to be what holds the cell in the telescope. Then it's going to hold this collimation apparatus. And then this will hold 18-point flotation and puck. So it'll be in the telescope like this and like this with the mirror here. And so you can see as light as this is, the whole scope is going to weigh nothing.
Jeff, is that aluminum or is that?
It is aluminum. This is square tube aluminum with 8-inch walls. And I'm going to powder coat it to some silly color. And I haven't decided yet. I think that's everything I brought to show up. Okay, so I have two 42s. They're both F3. The idea is I'm going to make one for me, and if I break it, I got a backup to work. If I don't break it, I got a backup to sell. So hopefully somebody will get another 42-inch. Any questions? Yeah.
Yeah, okay, it's not a question, but can you explain to everyone why you have so much detail in making a mirror sub to support a piece of glass? What's the big deal?
Okay, so you kind of want the surface of the mirror to be held to a 20th of a wave so that the wavefront will be held to a 10th of a wave. Now, 20th of a wave is 1/1000th of an inch. So the surface of glass is going to have to be a paraboloid to a 1/1000th of an inch. So if I just grab this glass, its own weight is deforming it by way more than a 1/1000th of an inch. And so we separate the glass into 18 sections, and we have a width system to hold it in a way that each of those contact points takes an 18th of the mirror. And so each one's only holding about that much mirror. So the mirror is that thick, it's only holding that much. It's not deforming it by more than a 1/1000th of an inch. Until you tilt the mirror over this way, now the weight of the mirror is going this way. If you held it this way, the mirror will potato chip on you. So that's why I'm going to have the pump in the back for the transverse forces and the 18 points for the longitudinal forces. I don't know if I answered your question or not. Overdid.
Basically, that deforms under its own weight.
It will deform under its own weight. Okay, so
That was the question.
the other thing, why would we go with a meniscus? The answer is, one, it's thin and therefore it only weighs 1/3 of what a telescope mirror weighs. So the mirror that thick, its own weight would deform the mirror. It's so much thinner that it doesn't have that much deformation. But now there's less material to hold itself, so it does deform. But it's shaped like a dome, which is really strong, so it doesn't deform. So, you know, you got all these trade-offs going back and forth. So the fact it's a dome, the fact it's thin, the fact it's got 18 points, the fact it's got a puck, it should hold it to a diffraction limited shape. The other nice thing about being a meniscus is when you have a warm degree, you take it out on a cold night, the glass will contract. It's only that thick in the middle, but that thick on the sides. The rate at which they contract will be different. So it's going to go from a paraboloid to something else. And then hours and hours and hours later, it finally comes to shape your observing size. It's no it's a water waste. So this guy being uniformly thick will contract the same, anywhere, preserving a paraboloid as long as possible. The one issue that Howard Bannock has solved, which is really cool, is we usually have the back of the mirror covered with some kind of wall and a fan. And the front is exposed to cold air. So the front gets colder than the back. And so since the front would contract more than the back, it wants to bend in like that, hyperbolize. And so what we're going to do is two things. One is I'm not going to cover the back so that it's also exposed, but it's still going to do that. So the other thing I'm going to do is the puck will be glued on right there. I'm going to have a screw that I can screw into the center of the mirror with just the slightest amount of force, which will push the center forward, correcting the hyperboloid from having the front come. So there's a lot to this. Fingers crossed it'll all work out.
I don't know if you made this point, but the back of the meniscus is curved as well.
It is.
Yeah.
They are both curved to F3. They're both curved to F3. The front will be a polished surface. The back is not. I usually polish the back of the mirror because I like the contacts on the cell that have the freedom to slide. But if I polish the back of this and when I test the mirror, I'll not only get a front reflection that comes to focus at the test stand, I'll have a back reflection that comes to focus at the test stand, which will completely ruin the test. So I have to leave the back fine ground, which I don't like doing, but because of my Hartman testing, I'm gonna have to do that.
Yeah.
The way out of that would be to silver the mirror every time a Hartman testing. Yeah, Dennis.
Curious, you're talking about having an adjustment on the back of the mirror. How are you going to tell when it's right? Are you gonna have some sort of servo do that?
Well, you could, but it's a piece of cake. When you look at the telescope at high power and the mirror is corrected, you have a star test that says my mirror is corrected. Now, if the mirror becomes hyperboloidal, you can see it in the star test. So either you or a really long arm person or a friend.
That's what I was
Very
thinking. Like that long.
Or turn it, look. But we're only gonna be, give me a hand.
Budget.
That much force on. And that's all it's gonna take to push the center that a millionth of an inch. And so you
took a picture.
That's okay. Leave it. Leave it be.
did I just do that?
Yes, leave it be.
Yeah. So, what I'll do is I'll put 1,000 power in the scope and screw that thing until the star test comes up perfect, then I know I'm correct.
Jeff,
Yeah.
those 42-inch mirrors seem like the eyepiece is gonna be way up in the air.
Got a way out of that.
So I'm not gonna climb a big tall ladder, am I? To get up to see it?
Well, you are, because you're only this tall.
Yeah.
That was a short tilt. Oh, darn, the camera's looking up at the sky.
That's okay. Don't leave it alone.
So here's the deal. Most telescopes have a secondary mirror that's set at 45-degree angle, shoots the eye.
Yeah, right here.
That shoots it straight out the side. And the secondary mirror is oblong. I'm gonna have a round, large secondary mirror. It's gonna be tilted at a different angle. So it shoots the light back at another angle, so it'll make the telescope a foot shorter. So instead of being 10 foot 6 inches, it'll be 9 foot 6 inches. How long is yours? 8 feet?
IP's height, you mean on the
Yeah.
ground? It's about 7.
Okay, so this will just be a little bit longer than mine, but I'm gonna have a ladder that's dedicated to the telescope. But, yeah, for 42 inch, there's no way out of not having some kind of ladder. But, and that's
Zenith. At Zenith, when you're looking down at something lower, like,
chances are it's still good. This is,
That scope doesn't work well when we're looking straight up anyway. We almost never look straight up. It kind of jams up.
yeah,
It's called Dobson's hole.
yeah.
So you want to look down into here anyway.
so, most 42 inch scopes are skyscrapers. And F3 is better, and then with a further tilt the secondary, it's even better. So 9 feet is actually pretty good for a 42 inch scope. But yeah, we're still, most people will be either a third or fourth step on the ladder, but it won't be the 17th step on the ladder.
Yeah.
Like Dan Dawkins and most of them, if you see pictures of that, it's insane. No way. Sorry, Dan, if you're on here.
No.
Okay, he's not. It's insane. That's too tall. This one's gonna be, you've seen how short my scope is, 32 inch scope. His is f2.84, this will be f3.0. Virtually twin telescopes.
Can I say a few things, Jeff?
Yep.
Yeah, probably maybe some of the people are thinking, well, why even bother with it? It's a heavy telescope anyway. But what I learned, as you get bigger, the telescope gets heavier very, very fast. And most people, once they get up to about a 12-inch telescope, that's the limit. They just don't want to go more than that. It's just too heavy to carry around. When you get to a 32-inch like mine and you're 450 pounds, it's a nightmare. And Jeff and I are older to begin with, but even if we were in our 30s and we were linebackers or the Raiders or something, it's still very difficult. So this is a huge advancement in terms of making large telescopes. Problem right now is just working the butts out. It's going to be a beautiful telescope to get it done.
Well, like Mike's scope, it will be motor moving. I'm not gonna be pushing scope. It'll be moving around with a motor. So here's another thing about bigger scopes. If you look at a spider, They got skinny little legs, but if you look at Velvet, they got big fat legs. Scopes are the same. You go from a 20 to a 40, that's a size ratio of 2, so the long and mass ratio of 8. So this will be 8 times heavier than the 20. And so now you have to engineer a lot of stuff to handle that kind of force. The poles are going to bend. The secondary mirror is going to be heavy. Just the structure itself, even though it's going to be lightweight aluminum, it's going to be a massive problem. Then you have all the thermal energy involved with that. It's going to be dumping heat all that. So that's an engineering problem.
And one more thing, if you think about it, the largest refracting telescope in the world is only 40 inches. Jeff's gonna have to beat by 2 inches, and that's gonna be a massive, incredible telescope.
Yeah, well, that thing weighs
Yeah.
100 tons, yeah.
Yeah.
Hundreds of
It's like much of the Sherman tank.
Jeff, that's amazing technology. Have you seen it all in practical use at this point?
Well, Mel Bartels and Howard Bannon, both of them giving presentations to our club, are using 30-inch f2.7 meniscus mirrors, and they work perfectly. I don't know of anybody that's gone 40-inch meniscus yet, let alone 42-inch meniscus. But I'm sure before I get this one done, they will. My friend over in Luxembourg has 45-inch, but his mirror is that thick. So there are some guys who are 40 to 45 inches, but the biggest meniscus I'm aware of is Howard and Mel's 30. And they're both 3/4 inch class, just like this. And they're f2.7. I was originally going to do 40-inch f2.7 because I can pull off an 8.5 inch minor axis secondary mirror, which I can make. But I can't do that with this. So I'm going to have a really huge 12-inch circular secondary mirror that's at a funny angle. And it's going to be an engineering problem because it's going to weigh a lot on the long end of the scope. You don't want a lot of weight on that end of the scope. And that's a problem. Like I don't have any problems.
You can do it.
Excellent. Thank you. Yeah, I can do it. All right.
By the way, Jeff, that was a $600 camera you got.
I don't even remember knocking that thing down when I walked through the works.
Yeah, God, yes.
Okay, Eric, let's start. Everybody enjoyed this show and tell presentation? That's pretty great, huh? We're so fortunate that we actually have 2 other presentations we're going to be watching in the coming months. Dennis has one of his trip to the Kent Observatory. That's going to really be looking forward to that, Dennis. And Agenbear has a presentation on exoplanets that he's put together. I'm looking forward to that also, Agenbear. So thank you both for the future programs we're going to see. Eric, when you're ready, let's go to the announcements. And by the way, when we adjourn, don't anybody leave the room because we've got mirrors to carry and telescopes to transport out to the parking lot, okay? We need all the horsepower tonight to get. Okay, just some quick announcements. All of our normal star parties are on the calendar this coming Saturday. Is the sky going to be clear? We're not. Probably not. For Highway 4.
Yeah, Tim, just as a side note, so Kasey, Rich, and I were up at Murphy's.
You were in Murphy's.
Clear sky. Yeah, it was high enough, clear sky, so don't know. Maybe I'll get lucky.
They showed on the news tonight, they showed a picture from 2,300 feet with above the clouds.
Yeah. Our elevation at Highway 4 is not that high.
Right.
Okay, new moon on the 19th for our new moon challenge people. And then December 20th, high altitude party. I won't get up to Pedley Hill, maybe to Heliport. They haven't been getting that much snow, so maybe we'll be able to to get to the heliport. The 21st is the solstice. For all you pagans that celebrate that. Coming up in January, mark this on your calendar, January 8th is our installation dinner. We're here at the Wentworth Center, but we're not in this room, we're at Harmony Park. Got another slide here. And then our star parties in January. January 24th is Astronomy in the Park. So we skipped December, we'll be back out there at the end of January 24th. So the dues are due, and it goes to Jerry. Use the mail-in form on the back of the newsletter. And like I mentioned, January 8th is the installation dinner. We have a guest speaker via Zoom. Eric, do you remember what Neil Farber talked about astrobiology?
Yeah, to be honest, I reached out to him on Monday, but I haven't heard back. So hopefully he's going to respond. I have a funny suspicion something might have happened to him, but I don't know.
Okay, let's follow up on Dr. Neil
Yeah.
Farber. We need that guy in January 8th. So, last year we had a potluck, which is great. This year we're going back to a catered meal. It's going to be $20. It's going to be catered by Papa Pablo's. We can have either a chicken or vegetarian dish. There's the time schedule. Arrive sometime between 5 and 5:30. We're eating promptly at 5:30. And then our program includes desserts and beverages. So we'll be sending out emails, and the January newsletter will also have all the detailed information and reservation for the dinner. We do need reservations, so we get the right head count on food.
Tim, what is our I forgot what is our deadline for the RSVP?
I believe I had put on there to get them in the mail by January 5th, because they're going to be mailed to Jerry.
Oh, but okay, so we will need to have just the head count for the dinner earlier than that. So they told me 5 days.
5 days, okay.
Yeah.
We might have to adjust that date then. I'll contact you.
Well, I mean, yeah, I know it's like 8/5. Well, yeah, that's pretty close. That's cutting it really close.
Yeah. Okay, very good. Refreshments. Sign-up sheet went around. Next slide then, please, Eric. The New Moon Challenge on November 22nd. I only got this from Ray. Ray caught the sliver moon in Elk Grove. Got shot, Ray.
Yeah, I failed. It was cloudy the whole time around here, or when I was around, I guess.
Yeah, Kasey, I was wondering if you tried or if you got that clouded out. But we've got one coming up December 19th. Hopefully we'll have clear skies by then. I think that's the last slide.
Yeah.
Okay. I want to thank all the presenters gave excellent presentations tonight. And Jeff, thank you for the refreshments. Everybody help yourself there.
Yeah, keep eating, guys.
And,
There's a scramble if you want to see the solution.
yeah, and in the newsletter, did anybody, wait, before you put the answers up, Eric?
Oh,
I already did.
yeah. I didn't get 3 of them. I couldn't get 3.
I didn't get 2 of them. They were tough.
No,
Eric, did you come up with these on your own?
I did not.
They were generated somewhere else?
They were generated, yeah.
Yeah.
what
You got dark matter out of graph for the grid.
I didn't get supernova. I should have gotten. I didn't get. And there's something at the bottom I didn't get. No, maybe.
They were pretty tough. The planets were pretty easy.
I got
Yeah, those weren't too tough.
wormhole, red one. I don't have it on me. Oh, Big Bang Theory. I did not get Big Bang Theory. That's a good one.
Oh, yeah.
I do admit that I did cheat. I found a word unscrambler on the internet. So just FYI, you can cheat. Don't encourage it, but it doesn't work for the multiple word answers, like Big Bang Theory, you want unscramble, something like that. Very good. Give us another one in the January newsletter. This is fun.
Yeah, we can try to. Yeah.
Real challenge. Okay, did we miss anything?
Now, I was just gonna comment, the word unscrambled will be really helpful if you get an email from me.
Yeah, about the second. That's it. So. Okay, let's adjourn, enjoy some refreshments and enjoy lugging all this gear, all this astronomy gear. Urvi, again, congratulations on your new telescope.
Thank you.
Look forward to seeing you out there. So, good night, everyone on Zoom. We're going to adjourn the interim.